Usually I don't do these types of episodes where I go really deep into a closed source tools, but I think it's really interesting what the guys at TopK are building, and I think they are building something similar to Snowflake, but for search, where they basically separate the compute and the storage for analytics in the case of Snowflake, and they are doing it for search. And they're building on some really interesting architectural patterns, which are more and more common nowadays. For example, using a log as a database, where you basically write all changes to append only logs first, and they establish the exact order of operations. They can be replayed, and you have data durability. It comes with a little bit of performance downsides, but it gives you a lot of advantages. But also things like a custom file format, as we have seen in, for example, LanceDB, but also something we are seeing more and more like custom table formats in Iceberg and Data Lake, where you control how the data is stored and laid out and organized on disk so you can get more performance out of it, and that you actually get it performant enough so you can utilize really cheap object storage in the cloud, like S3. And then they also build their custom query execution engine. And the query engine basically turns a user request into something that's more optimizable and understandable. So basically it parses the query, creates a logical plan, pushes down filter, distributes the work across nodes, then the computation happens, and then you merge the results back in and return them. And these three components, I think, are really interesting as a more general trend in all of data. And in this episode, we are talking to Marek Galovic, who was a former engineer at Pinecone and is now building a new kind of search database at TopK. And we will be talking a lot about how they built it, their architecture, but also the different decisions they make that went into building a search database from the perspective of the 21st century, like all the new hardware and architecture components we have access to, like really large scalable storage, really efficient compute, way faster IO than what we used to have. And I think that's a really interesting discussion. And also you can take a lot from it, even though we are talking about something closed source. Let's do it.
One super nice thing about like building distributed systems, like building distributed algorithms with Rust, is like precisely the async ecosystem, where like Rust itself doesn't have an async runtime. You can provide your own runtime. And there's this project from Tokyo called Loom. And what you can basically do is write your concurrent program as async, right? So like if you do any sort of network communication, all of that, you would write that through async. And then you can use a deterministic runtime to simulate all the possible executions of those futures. And that allows you to basically like specify a formal model for like how the system should behave, assert all the invariants, and then essentially simulate your distributed algorithm on top of a single node, which like makes testing much more robust. And like we can actually like test all the possible cases.
Why do you think Milvus went mostly with Go instead of Rust to build like a cloud native vector database?
Before Rust, Go was like the default choice for like new systems languages. Like when I like back then, like 4 years ago, when I built my like open source vector DB, I built it in Go. Like it was a pretty good choice for like new sort of systems languages that are simpler and like have better ecosystem than C and C++. But then like Rust matured a lot over the last 5 years, so I would say like Rust is now becoming like the default choice.
Yeah. And maybe to kick it really off, can you maybe quickly define what is a query execution engine actually?
So like basically you have a sort of description devices, like you have a description of like what needs to happen, right? Like that could be a SQL query. And then they have a bunch of data in some format. And then the query execution really takes that sort of description of what needs to happen, compiles it to some sort of set of expressions for that data format and for what it actually needs to happen on the physical layer. And it drives execution, drives the IO, drives the computation to compute some result and give it back to the client. Something like a super high level.
And in your case specifically, like How does it work? A specific query is coming in. What's happening behind the scenes to actually go from the query to the final search result?
Yeah, so the API we expose is very like data frame. So we provide an API that's a bunch of stages that describe what needs to happen. Really, what happens is that we build like a distributed query engine called Reactor internally. And then what happens is the sort of the routing node or the client facing node gets the sort of public description of what needs to happen, translates it to a logical plan, which is a sort of internal description of all the operators. Then does like some optimization of the logical plan, right? So like we want to push down predicates all the way to the scans. We want to push down projections to only read the columns that we care about. That happens still on the router node. And then since we have a big data set, we distribute the sort of parts of the data set to different executor nodes and send this plan to the executor nodes. And then like executor nodes, since the model is more document oriented, so like different files can have different schemas because we don't require you to specify schema upfront. And so then the sort of logical description gets compiled for a specific plan on the like for a specific file on the executor node, and then we drive the execution. That really dispatches operators onto TopK runtime. We compute partial results, right? So like every node does its own part of work. Then we send the result back to the router node, which also like pipes those results. So the same execution engine really is like Reactor running on both, and then returns the result to the client.
And within that, what are the morsels or small pieces of work that you're doing? Can you give an example?
Yeah. So for example, like if you are doing like vector search, one of the morsels is like you have a block of data, which is like a part of a file, and then you want to compute like sort of cosine similarity between like vectors or projections in that block of data in your query. And so that morsel is really give me like cosine similarity on 10K rows.
Yeah. And you mentioned in our previous conversation that you have created your own custom file format.
Yep.
What makes it better suited for search use cases than, for example, like Arrow, Parquet, and what we have currently are also Lance?
Yeah. So we build a database to be like cloud native and really like use object storage as the sort of primary storage medium. And then, like object storage has very different characteristics compared to like locally attached disk. Right? You're like spinning disk or SSDs. And that way is like your request latencies are like 100 to 200 milliseconds, P99. And then like you also pay per request, right? So you don't want to do too many small requests because that's super expensive. So you kind of want to take that into account, like to take latency into account, and then find optimal, like issue optimal request sizes to maximize throughput and minimize costs. And like really the issue with like off-the-shelf format, take Parquet as the default, is that Parquet really couples like the IO size, IO execution with the statistics, right? And you have like in Parquet you have row groups, then within row groups you have column chunks, and within those you have pages, and the page really is the sort of unit of IO. Issue with using that for search is that basically if you have like a bunch of columns, and one column is like float32, right, or U32, like some small value, and other column is like say 768 dimensional vector. You will have if you read the whole column, it's gonna be like 40 kilobytes for 10K rows, versus like the sort of vector column is gonna be a bunch of megabytes. And then since you're issuing IO on that granularity, right, you will do a very small request for the scalar for a file, so scalar field, and then like huge IO for the vector field. And that's an issue. Like you want to have very small pages because you want to have statistics that are very granular to do pruning very efficiently. But doing like but also like you want to, for the case of U30 field, you want to maximize the size because you want to avoid doing very small requests. And then coupling the sort of statistics granularity to like IO granularity is an issue for doing that on top of blob storage. The other issue is like Parquet was really built for spinning disks. And so if you like read Parquet file, you have a lot of serial dependency of like, I need to read the footer, then the footer sort of gives me a pointer to the schema gives me a pointer to a bunch of like block indexes, and then I can read the actual data. That's like serial dependencies where each of those is 70 milliseconds to actually get the data, right? For object storage, like you want to do a lot of concurrent IO, and like we build the data format to really have like wide IO trees where we can read some small amount of data and then issue a huge amount of concurrent IO to actually pull the data very quickly. So those I would say like two biggest differences. You also mentioned like building a sort of a custom file format for search. We actually like use Arrow as our like data layout, the primary data layout, and also like the in-memory layout for execution. Although we extended Arrow with custom layouts to basically support types like dense matrices, sparse matrices, and bit-packed posting lists to optimize for the use cases that we really care about. Like if you co-design the layout with the execution, you can basically do stuff like execute the kernels on top of compressed data. So you don't really like need to decompress, for example, posting lists. You can do the actual compute on the compressed representation.
Yeah, and in search you usually pre-compute a lot of stuff. So you pre-compute all the indexes, all the statistics of the different documents. What things are you pre-computing, and where are you storing it? Are you storing it with the row groups, with the files, with the column groups?
Yeah, so we do pre-compute like more efficient representations of vectors, for example, to make the scans much faster. We pre-compute inverted indexes for like keywords and keyword search. It's not really pre-computing, but for example, if you store float32 or you store string values, right? We do dictionary compression to actually make that much smaller and make the sort of predicate evaluation much faster. So this is the sort of stuff we tend to pre-compute. In terms of where we store it, it depends. The having a control over the file structure allows us to basically store the columnar data as columns logically, and then attach external indexes. So, for example, like inverted index for keywords is attached within the same file, but it's like a separate from the column data. And like the query execution then allows us to basically take the columnar data, take the external indexes, and basically intersect the query and execute the query on both in the same pass.
Nice. That's really interesting. And how do you actually handle distributed queries? So you have multiple files stored probably in different locations. How do you
Yeah.
distribute it and be sure that you actually have the correct statistics in all the different files? And also be sure that you can find like all of the different search results.
Yeah, so maybe like to answer this question, it would be helpful to go over like the high level architecture of how the system looks like. So we follow the approach that database is the log. So when we get it right, we append it to a write ahead log. And at that point, once we acknowledge that, you can be sure the data is durably persisted. And then on top of that write ahead log, there is a indexing process that tails the log and builds more read optimized representation of the data. And those are the index files. And basically, like the sort of description of what are all the index files is a manifest where we store pointers to every file in the index, and that the manifest really is a sort of like a consistent snapshot of the system at the point in time. So if a indexing process fails, we can just load the most recent manifest and pick off where we left off, or pick up where we left off. So that like the guarantee of consistency, we always have a consistent snapshot of the index. And then in terms of like how we execute distributed queries, like the router node loads this manifest, which is the description, figures out what all the files are, maybe does some like high level pruning to exclude the data that's like not relevant for the query, and then takes the files that are relevant, distributes them over a set of executor nodes, and then what I mentioned, the reactor framework that takes over and runs the execution on top of the sort of the executor nodes.
Yeah. And do you actually redistribute the data? So, for example, if certain pieces of information are often retrieved together, that you actually redistribute the data. So, similar data that's retrieved together is actually co-occurring in the same files or and same locations.
Not really. Like we try to minimize the assumptions on access patterns, which like is an issue with the vector DBs, right? Because they assume like the locality is there in the vector space, whereas your queries are usually all over the vector space, not necessarily coalesced together. So we like remove that assumption. In terms of like how data is organized, we like the storage engine really is like an LSN tree. So the data is sorted by the ID. And so one access pattern that's very common is that like people want to store like multi-tenant data in the same index. And a way to do that very efficiently, like with our system, is you basically prefix the ID with the tenant ID. And then once we sort by the sort of user provided ID, all of your tenant data will be coalesced together, right? And so then you can issue a query that, hey, give me all the sort of data I want, subject to the ID starts with this prefix. And then we can like prune all the files that are not relevant and basically just get the file that's like contains the data that you really care about. So in that sense, like it is coalesced, but we don't regroup the data based on the query patterns.
Yeah. And you also mentioned you're using a cache on EC2. I'm really curious. What's the caching strategy? Like, how is it determined what stays hot, what's evicted, and how do you actually handle also the cache consistency?
Yeah, so like specifically where what we cache where is like part of the secret sauce to give us like good latencies and low cost. But on the whole, like the in terms of like eviction strategy is just LRU. Like that works really well because you are basically caching blocks and like you want to prioritize the data that's like most recently accessed. We have the option to ping customers in the cache and provide a dedicated capacity, but for the like the shared cluster, it's LRU. How the caching works specifically, it's two tiers where every executor nodes caches both in memory and on disk. And then the blob storage, sorry, the blob storage is a sort of durable layer. The grounding of what we cache is that the sort of data format has a bunch of buffers. And then we cache on disk, like we cache buffers, which could be like multiple columns or like multiple unrelated pieces of data. We like at the right time we try to sort of coalesce relevant data together into the buffers. And then in memory, we cache like smaller granularity that helps us like prune a bunch of data very quickly, execute the first layer, and then minimize the amount of data we have to read from disk. That's like how that works.
Yeah, and I think most vector databases, when actually run like two retrievals, so the new data which isn't indexed yet is like basically brute force vector searches run, and on the
Yep.
older data you run like your HNSW index, whatever.
Yep.
How do you approach the same problem, like of eventual consistency in the end? You can only run the retrieval when it's actually indexed, but also for the different types of search you support, because you have the BM25, probably the classical term search, but you also
Yep.
have the vector search.
So in terms of like consistency models, we support three consistency models, which is really two and one is masked. We do support strong consistency. So if you like write the data, any client in the system can actually read that data if it provides I want a strongly consistent read. It's more expensive because we have to check what's really the latest data against the source of truth, but we can do that. In the default mode, we propagate the write within a second, right? So if you write your data, that write will be visible. Like the max delay there is like 600 milliseconds, so it will be pretty much there right away. And then that sort of needs to query the data that's not really read optimized yet. And then for like high performance and like large scale use cases, they don't necessarily care about like data latency that much. Like usually just have some background job that writes the data into the index. And so if you want to get the best performance, you can provide indexed mode, which skips the most recent data and only reads like the read optimized representation. That sort of gives you the best performance, but the delay there is like a couple of minutes.
Yeah. What are the different use cases you have seen for the different consistency mode? Like when is actually like strong consistency necessary?
Yeah, as I mentioned, like for like large scale use cases, that are not interactive. The indexed mode is the best choice because like you get the sort of the best performance, and you can like load the data in an async job. Like that's not user interactive, so like it's not a problem there. The use cases for the default mode that we provide, and then the strong consistency is really like interactive application. Imagine you're in the notebook developing your search. Really, you don't want to wait 10 minutes after you write your data to like, now I can test my query. The default mode is really the best suited there, where you have a bunch of data, and then like when you go run the query, it's there. And I think the default and strong consistency modes are really becoming super useful for agentic applications that are interactive with the user. You want to provide memory for your agent or whatever, and then you don't want the agent to not remember for 10 minutes and then the memory shows up. So if you are interacting with the agent, like you want to get a result right away, like doing like either the default mode, if you are fine with the small delay, or doing like a strongly consistent read is super important there because like you're guaranteed to get the most recent write reflected in your query.
Yeah. I think one often like underappreciated aspect of Elastic and the other search database is like the analytics. Do you already have implemented like a custom data format for the feedback data and the analytical data as well?
We don't have a custom format for any feedback yet. The data format that we built is suited for analytics. So also like the query engine, right now we optimize for search, but it's basically like a matter of adding more operators to support stuff like aggregations, to support metrics, to support stuff like that. Because really, in the end, it's like an execution engine on top of columnar data, right? We optimize for something, but basically you can add operators to support other types of queries. One side use case for building a very good filtering engine and general query engine is that like log search and basically like security and observability is a sort of a special case of search, and we can like also like support use cases like that very efficiently.
And can you actually fall back on data fusion a little bit more for the analytical queries?
Not really. Like the execution engine is a custom engine. We looked at data fusion early on, and basically what we realized is that like data fusion is very good for analytical queries. That's what's been built for. And like a lot of like new databases actually use data fusion as their like execution engine. The reason why it doesn't really work for search is that like data fusion doesn't support external indexes natively. Like the way you implement indexes in data fusion is that you basically build one side of the join and then you join your data with the index, right? And like building that one side of the join is pretty expensive. And if you have control over the data layout and execution, you can basically do like a sorted intersection of both and then execute the sort of index scan and data scan much more efficiently. Like that's like the primary reason why data fusion doesn't work. The other reason is like what I found is filtering in data fusion is really like it's rebuilding the batches, right? So if you filter, you basically like copy the data into new batches and then continue execution on top of that. Versus what we can do is essentially execute filters as logical operations where if we know that the data is already cached in memory, like there is no point of copying the actual data. We can simply create a new selection mask or bit mask on top of that data and then continue execution using that. But yeah, like on the high level, like basically you get 3 to 4 times better performance by not using data fusion for search.
Yeah. And you mentioned also in our previous conversation that you have built some custom error extensions for dense and sparse matrices.
Yeah.
What do they actually enable you to do?
So one like huge unlock there is that in like vector DBs and most DBs, like you would have like vectors cannot be null. You have your index and like you have to provide the primary key for the index. Since our model is more document oriented, you can have a bunch of vector fields. We really treat it as a data type. And those can be null. We don't require it to always provide the value for a field. And so one biggie unlock for having the data, custom data layouts is that if you want to represent, we can represent nulls very efficiently without actually storing dummy values. And then also be able to do point reads for those rows that can be null and may not be null. Like the sort of the compression in the way you represent that, the way you figure out where the value actually is in terms of byte offset. Arrow like stores an offset list, which is U32. Like the way we figured out how to do that is like basically like 20 to 25 times smaller, which like really means for like a file of 10 million rows, right? We're not reading just 40 megabytes of like dummy values, where like you can basically read 100 kilobytes and do the same. There is no overhead of that. Similarly for like sparse matrices, and I also mentioned like bit-packed arrays. Like Arrow doesn't natively support bit packing, like bit-packed arrays. Also, it doesn't support sparse matrices to basically optimize for sparse matrix vector product. And so we built custom types to compute those types of scores very efficiently.
And what other advantages do you actually get from the arrow format? Does it actually help you with a distributed system as well?
Uh, it doesn't necessarily help with distributed system. Even if you look at data fusion, it's like a lot of the value of data fusion is that it basically uses Arrow and Arrow compute kernels to do like undifferentiated stuff, right? So like filter floats, like every database needs to filter floats. Every database needs to like filter strings. That's not a differentiation you need to like care about and spend like engineering time writing kernels for that. So like we get a lot of that by just like simply using Arrow and like skipping the data fusion part. And that's actually like what we get. Like the custom types, like we write custom kernels, we optimize them for different architectures. That's the sort of meat of the database. Versus filtering floats, filtering strings, like doing undifferentiated ops, like that we can just offload to Arrow and use their compute kernels. And like that's a sort of huge time saving.
And the manifest files, maybe to double click on that.
Yeah.
I've mostly worked with Delta and Iceberg, which basically have JSON files. Partly why they do this is because on S3, it's like there is a limit of how many files you can list. So you usually have manifest files, so you can list all of them at once. How do your manifest files actually differ from, for example, Iceberg and Polars?
Yeah, like on a high level, it's very similar because
Yeah.
if you're building a database on object storage, like you tend to make similar choices in some regard. The difference there is that, like as I mentioned, like we are document oriented, not necessarily like table oriented. So we don't really enforce schema or store schema in the manifest files. And we have just one manifest file for the whole index. The sort of huge unlock there is that Iceberg, you mentioned like it's JSON files. What we've built is basically we use flat buffers as our like format for describing what exists. And what that allows us to do to basically just read the data and interpret it, right? So we don't have to decode JSON, we don't have to cache it in a special way. We simply load the bytes and then use flat buffers to know what's indexed. So that's a huge saving, especially for large indexes, because you can, if you do JSON, like you can end up spending like 600 milliseconds just decoding the manifest. That's like all of your query budget pretty much. So like by not spending 600 milliseconds, but like only paying the IO once and then using the data, we can basically minimize the sort of worst case latency that happens.
Can you also enforce any asset properties with your execution engine and with the file schema?
Yeah. So as I mentioned, like the writes are like atomic once we commit them to the
Yeah.
Rerankers log. And the way we build the write ahead log is that it basically provides sequencing. So we know like at the time we commit write to the log, we know like a version of that write. And then basically that's the write that's the most recent version that will win. And then the compaction and indexing part consumes the log and uses those versions to enforce what's the newest version, right? So we at the time we commit a new version of the manifest or publish like a new version of the index, that's like a consistent snapshot of the database. So that like moves the state from one version to a new version. And there is no sort of way to see partial results in your queries.
Yeah. Is the. No, I lost my question. Does it also give you the capability to do basically a history? So I can go versions back in time
Yeah.
and run my queries on all versions of the search database.
In principle, we could do that. You could specify, essentially, you can imagine every manifest being a snapshot, right? So
Yeah.
we don't expose it right now, but we could expose like all the snapshots that we created and maybe keep the last day of history in the manifest. And then you could choose, okay, I want this snapshot of the database. And then, yeah, given it's a consistent snapshot, we could just run a query against that snapshot and you would get that version of the data.
That's really cool. And what I'm really curious about is in terms of kernels. I think Rust doesn't have all the like decades of optimizations which went into C and C++. Have you done any benchmarks of the performance impact this has? Because like in AI, this is like all the talk, like why aren't we using Rust? Like we have
Yep.
decades of optimizations in C++. Have you tried to quantify that stuff?
Yes. So in terms of kernels, we've handwritten SIMD kernels for the operators that we care about, right? For
Yeah.
example, like how to intersect a big tagged list for text search, how to very efficiently compute distances for vectors. All of that, like we've written custom kernels for both x86 and ARM, so that allows us to like basically run on the cloud. Like ARM nodes are much cheaper and like usually gives you better performance. So you can pick the architecture that you want to run it, and then yeah, we have kernels to sort of compile for that specific architecture.
Yeah. And do you think Rust is faster or C is faster?
It depends on the use case. Like all of them dispatch to LLVM ultimately. It depends on the compiler. You can get the same performance as C or C++, but basically doing what we did, and you basically wrap an unsafe code in a safe interface, and then in an unsafe land you can do whatever. So what we did is written, which is like the instructions for specific architectures, and that's
Yeah.
like basically as good as you can do.
And in terms of scale, what is the largest data set you have tested TopK with? Like, how far did you try to push it?
Yeah, so far from a single namespace, like a single data set, we pushed to 100 million, but basically like we've been doing that for 3 weeks in a production scale. With the latencies there being like on the 100 million scale is around like 200 milliseconds P99. For smaller indexes, which is like most of the tenants in the system, that would be like 1 to 10 million. And there the latencies are like around 50 milliseconds P99.
Yeah. And I think Milvus is at the moment doing a big push into doing GPU acceleration for vector search as well, but also for
Yep.
the indexing. Is this something you're already exploring, or that's like on the horizon for the future?
I mean, we looked at that. It really depends on like the use case you're optimizing for. Like GPUs are quite expensive, and if the operating point that you like want to get is like order of hundreds of QPS with a reasonable latency, so like say 50 to 100 milliseconds, you don't necessarily need GPUs for that, and you can get like very good performance there for pretty low cost. Same goes for indexing. Like it depends on the kernels you write and the sort of algorithms you use. But so far, like we did a bunch of cost estimations, and we haven't seen like a value for GPUs. But
Yeah.
I guess like it depends for the use case, right? Because if you have a trading algo or like a recommendation system that needs to do 5,000 QPS and needs to do that in 1 millisecond latency, doing like HNSW stuff, doing like graph-based algorithms or doing like GPU accelerated compute, it makes sense there. But the truth is like those types of use cases are like 1% of all the use cases.
Yeah. What is the use case you've seen, or would you say, what is the use case that is like the perfect one for the search database you're building?
I would say right now, the use cases we target are really the ones where getting super relevant context or results is critical. And that would be like financial, healthcare, legal use cases. And the primary reason for that is that like you want to be able to do like different types of retrieval in the same query to basically say I want to get semantically similar results that also like satisfy these like text filters and sort of metadata predicates. I then will apply custom scoring on that using like different vector scores and maybe BN25 cooler in the same query. And really like most of the existing search systems, the way they do it is you have separate indexes for maybe different sort of vector fields, then you have a separate index for text. You get partial results, then you do something like reciprocal rank fusion on top of the partial results, and then return to the client. I think that's the way to do hybrid search with the current technologies. The current engine that we built and the system that we built allows you to do all of that in the same query. So you can basically do multi-vector search with a BN25 scoring, and then apply like a custom expression to actually compute the TopK input, and then like score based on that. And really, what that allows us to do is, for example, one use case we've seen is there's a medical search, and what they do is they retrieve like passages from journal articles and then overfetch that and feed that to a re-ranker. Right? But the reason why they overfetch is that they want to boost some articles by like their score for how good the journal is. And really, there's no way to do that in the vector database that they're using. So they overfetch results, then resort based on the importance field, and then feed that to the re-ranker. That's not necessarily the best you can do, right? Because you can imagine some articles being super important, but not really having on the basic relevant score on the vector system. That wouldn't pass the first TopK, even if you overfetch. And with us, what they can do is basically move that sort of custom scoring function into the database itself, where the candidate set that they get is the best one based on the custom scoring function, and then feed that to the reincarnation to the user. That they can unlock to give them better relevance out of the box.
Yeah, not just better relevance, but also like often at the moment with vector database, I think like a lot of filtering. If you have to do post filtering, a lot of the times I've seen that the use cases actually need you to extract informations after the search. And when you have to deliver a fixed set of search results, it's like a real pain because often you end up like you have to run another retrieval in
Yep.
which you have to exclude all the documents which you already retrieved.
Yeah, most of those are like 2 or 3 years ago, like there was a sort of huge push. Oh, we do pre-filtering, we do post-filtering in vector DBs. Truth be told, most vector DBs actually figured out how to do some form of pre-filtering in the database, so they can filter the results. They can. It won't happen that you get empty results, even though in the database there are results. Because they pre-filter before the TopK operator or sorting with limit. The issue there is that usually the distribution of vectors and the distribution of filter values are uncorrelated. And so what happens is that you apply your filter, and then you have to scan large part of the index anyway, because the filter selects points at random basically in the vector space. And like that's a huge waste if you think about it, because like you spend all this effort indexing the vectors, you spend all this effort like building IVF style index or graph-based index, and then at the query time, like you basically end up scanning most of the data anyway, which is like slow and wasteful. I think that's like a fundamental issue with building a database around like a vector as a primary key, or like around the vector index as a primary concept.
And what are the knobs you actually expose, or the levers that you expose to the user, which allow them to basically fine tune or optimize the search for their specific use case? Like on top of the standard, like I'm running a term search and I'm optimizing it, I'm doing boosting of certain terms. What are you exposing to the user to optimize the search performance, but also the search result performance?
Yeah, so actually, maybe it's a sort of different way of thinking about it because we don't really expose knobs. Like the query language we expose allows you to write any arithmetic expression you want for scoring, right? So you don't have, hey, boost this specific term by 5. It's really like you can write an expression that gives you a numeric output and then score by that. So use flexibility, almost like a programming language, like you write some expression that gives you some number, and then you can score by that, which is very different compared to, yes, I have some keyword filter, and then I specify just a fixed set of boosting parameters, like that would be the case in Elastic. In the other knobs, what we do expose, you can, of course, provide different vector types. So you can filter it to, you can scalar quantize, you can do binary quantize. You'll be able to do like sparse vectors very soon. So those are like the vector scoring functions. You can compute BM25 scores. Those will be the parameters for BM25. And you can tune that. But what we really want is off the shelf. It should be like super simple and super intuitive to build production level search. And then you can play with scoring. You can play with stuff to push it further.
Do you want to integrate learning to rank into this as well? That you actually can come up with the basically the expression in a more automated way?
Yes. Ultimately, if you think about like how actually production level search systems work at like large companies, usually have some document transformation. Like today, like that would be embeddings. You can imagine like more ways of transform documents. You have a query understanding module, which sort of takes the query and transposes it to some sort of domain specific DSL. That would be like a query language. And then you have like on the output, you have ranking. And really, like the job of ranking is to take a set of candidates and resort them to some measure of relevance that's very domain specific. And that, like today, you can get like Rerankers from Cohere, from other companies. You can get open source Rerankers, but that's really trained on like public data sets. Right? That doesn't really mean that this is the best relevance you can get for your domain or like for your specific application. And so, like ultimately, in the end, what we want to do is provide this like all of these pieces in the same API with the ability to like for the applications to provide feedback for, hey, this item was clicked or this item was added to the cart. That's a signal you can use to optimize the ranking further. And then like you can basically create application specific rankers inside the database itself. And that's a place where we want to get in the end. That's the sort of ultimate goal.
And I think it's really interesting. I think the learning to rank part is something that's a little bit, it's at really large search organizations. It's done a lot, but it's not really talked about. And I think it's a really easy addition to the search stack because usually it's some form of boosted machine learning model, which is really easy to deploy and optimize as well.
Yeah, it's a spectrum. For simple models, there's a linear models that combines, I don't know, similarity scores with BM25 and some pre-computed features you store. That's a sort of linear regression function. You can express that already in a query language. So it's an arithmetic expression you can just express. It will work. For more complicated rankers that are like learned and use, I don't know, you still can do that. The issue there is if you want to provide a good out of the box experience, you need to be able to improve the model from small amount of feedback. Yeah. And that's like a core research challenge for how do you do that where like you don't have much data, but you want to have like strict improvement on the like baseline ranking model you provide out of the box. And once we can solve that very reliably and be sure that we can provide a good experience, we will put that in as a part of the query language.
Do you already have any research directions you want to explore for doing that?
Yeah, so for doing that is like really how do you improve off-the-shelf ranking models? You want to have a good baseline experience. So even if you don't provide feedback, like we want to be able to, the re-ranking part of the query language should give you better results. But then how do you take that and make it strictly better, make it a Pareto improvement, given small amount of feedback? So that's on the ranking side. On the document transformation part, I think there's like really interesting research and like improvements you can do on training like hybrid dense and sparse embedding models. And basically, given that we can do both types of retrieval in the same query, like we can actually learn the sort of optimal combination of the two to maximize the sort of relevance of candidates that we get. So that's like the second part of research we want to do on the input side.
How do you think about because we are in a document model, updates to fields are tend to be pretty easy, but updates to an entire column. So basically, when I'm introducing a new embedding model, I fine tune a
Yeah.
new one and I want to basically re-embed all of my documents. How do you actually handle these like bulk or mass updates? Especially also in light of like we are in production and we still have load running against our database.
Yeah, so if you want to switch to a new embedding model, one way to do that is to basically create a new column, reinsert the data with that new column, and then basically switch your queries from the old column to the new column. That's a way to do it. In general, this is a hard problem because if you build a database on object storage, the files are immutable. So the only way to really change something about the files or even a specific column is to rewrite the data. Like you have to pretty much reinsert the data yourself. In the long run, once we actually manage the embeddings for you, which is something like we want to do where like the interface is really text, it's not vectors. Because I think that's like a better experience. Like ultimately you care about like searching using text. You don't care about like vectors is just a technology. Yeah, we use that, but like what you care about is the sort of higher level interface. Then once we do that, we will be able to evolve the embedding models, evolve all that underneath in the database, and you don't have to necessarily worry about it.
Yeah. How I think the part why Elasticsearch is still so popular is actually like the way of doing relevance engineering. Like they have very good feedback functions where you see the impact for a specific query. How do the different terms, how do the different parts of my relevance algorithm, my scoring algorithm, how do they impact these sets of documents? Do you provide a similar mechanism for basically debugging or analyzing the relevance and performance of the search queries?
In the query language, I encourage people to check out how the query language looks like, but you can basically select different parts of your scoring, right? So you can create separate fields, right? Vector, BN25, some internal fields, and then do the final sort of expression in the TopK operator. And then you can see what is the contribution of individual parts in the final scoring, because you will get the partial scores and the final score as a part of the output. So you can see, okay, for this document, the vector summative is really good, but BN25 score is pretty shit. For other functions, maybe my BN25 is really good, but the vector summative is pretty low. And then you can actually fine tune that and see what the contribution is.
Yeah. On part of the documents, because you mentioned the documents don't have to have the same schema. When I'm running searches with filters, what is handled like when the field isn't existing? Does the user have to set whether to include it or exclude it?
Yeah, by default, we evaluate only for fields that have the value, which is, I guess, the most intuitive way. And you can provide like is null operator where if you want to include, hey, this field must match this value, or it can be null. Like you can actually express that as an expression.
Yeah. What's next for you guys? So what are you building on at the moment that you can already teaser?
Yeah, so we have the storage out, so you can already play with that and like experiment with it. The next part is really like adding the more of the end-to-end experience, right? So as I mentioned, like the sort of really the production search is document transformation, is query understanding, is ranking. And we want to build all of that in the same sort of API where like today, if you want to build semantic search, like you have to build an embedding provider, create your embeddings, then you have to like store it in some database, retrieve that, send it to a re-ranker. Like that's an unnecessary like plumbing and boilerplate. Like if you look at any guide, like how to build semantic search, like it's all the same modular, like the last sort of paragraph, like you insert your own product. I don't think that's a good experience. What we really want to do is build this into 5 lines of code, and you should be able to use text really as an interface, and not necessarily like care about okay, this is embedded somewhere, this is re-ranked somewhere. So that's like the immediate next step. In the long run, as I mentioned, like interesting research on like how do you do hybrid embeddings, how do you do tailored specific like domain specific ranking, how do you adapt rankers and small amount of feedback. This is right now is like in research stage, but like somewhere we're gonna definitely go to.
Yeah. What would you say is missing in search or AI that you're actually not building on?
Yeah, I don't know. Like one thing that's very interesting is integrating like search with the LLMs on like a lower level, right? So today, if the context is provided as text, like you can imagine injecting context in different ways. Like really, attention is in like LLMs or in transformers, is doing search over the weights stored in the model itself. And so you can imagine like injecting context on the sort of embedding in like the latent space, not necessarily in the input space of text. So it's like a research direction I think is interesting from like a purely research point of view, but training LLMs and doing that is not really in scope for us.
Yeah. And maybe even like underhyped, overhyped. Like in the AI space, what do you think is underhyped and what do you think is overhyped?
Overhyped, I think like LLMs themselves, like in the long run, I think they just become commodities and you like different providers converging to the same point. This is hard to predict, right? Because there can be a breakthrough that sort of like unlocks a new capability that like no one foresees. For underhyped stuff, I think like verticalized AI, so building AI for specific domain and specific use cases, where I feel like there is a lot of interesting work happening, like applying AI to like biomedical data, applying to like material science, where like training models there really what it unlocks is basically speed of iteration. So if you really want to get far, like you need to fail a lot. And today, like failing in the biomedical domain or like material science, where it means like building the thing, which takes a long time. So I feel like having good models there and being able to use models like experiments and run experiments on unlocks you to try a lot of stuff in parallel, try it very quickly, and really like scope down to the subspace that really matters, and then go and do physical experiments just on that subspace. And like it's really nascent. I feel like AlphaFold is the first example, like first production level example in that space. But I think there are like many more coming in the coming years,
Yeah.
and it's super exciting. Like it's gonna be a huge unlock for so many things.
I'm so torn on the LLMs are overhyped. I think they are definitely overhyped, but I think they are still underutilized.
Oh
So
yeah, for sure. Like they're super useful. It's just the making them like omnipresent in a society like a workplace. That's gonna take a bunch of years. It's
yeah,
there's a lot of
I think like we're skimming the top off at the moment with LLMs,
yeah
and I think we will see like a lot more stuff at some point, but it will take a lot of time, especially in the enterprise.
yeah.
Nice. And where can people learn more about you, about TopK, and what you're building?
Our website TopK.io. You can feel free to visit that. We have a bunch of guides. We have docs. You can sign up and try us out. For myself, I'm on Twitter. I'm on LinkedIn. I do my name, so people can like reach out there. I'm happy to chat.
So, what can we take away from this that's relevant for our applications? I think because it's a little bit different to our usual episodes where we share like concrete advice, we went really deep into how they built it and how they designed their tools. So, I would take away more like patterns for building data search AI systems. And one of them is basically separating write and read paths. So especially like in databases, you often have a trade-off, optimize for writes or reads, but not really both. And Logbase really can give you a little bit more like flexibility in optimizations of actually exposing it to users, like what is he optimizing for. And they basically have done this by giving him the user different consistency models, so basically strong, default, and indexed. And through that, the user basically can choose between what he's optimizing for, whether it's read or write. And I think thinking through the trade-offs of your system, and often like when you're in data and AI, it's read and write, like thinking through it, like what are the knobs I can turn to optimize for one or the other, and what trade-off am I going for, or what trade-off do I want to allow my user to optimize for, is a really interesting one. And we see this pattern across a lot of different databases. For example, in Kafka, or data systems. In Kafka, you have events that are written sequentially. Also in CI/CD, I think you can draw a parallel that you commit code to a main branch, and then from that you build optimized artifacts for deployment. The design for your storage medium is something that is also pretty interesting. Like S3 and cloud storage, they aren't just like slower disks, they are like very different economics. And depending on the cloud you're building on, you have very different economics or pricing structures. And taking that into consideration as you build your application is probably relevant. Because in most cases, you probably have external constraints which determine what cloud you're building on. And if not, you should think about like how you use your storage medium and then pick the according cloud provider, because mostly storage and egress and ingress are the major cost drivers. And in S3 and cloud, you have really expensive egress and ingress. And when you make a lot of requests, so basically you pay per request, so having a large number of requests is really expensive. So having something like a log and then writing after a certain time periods and basically combining or batching the writes really pays off, because you can save a lot. And also for example, Cloudflare, I believe, doesn't have any egress and ingress fees, but they charge differently. So they probably, I'm not sure about Cloudflare, but they probably charge more based on the storage. So I think like when you design from the get-go for your specific storage medium, you can optimize a lot in terms of costs. Also, what they do is basically combining multiple things into one, which usually run through different systems. They combine vector search and text search into a single pass, whereas most search databases see it as multiple different types of search, which are then merged and re-ranked. And this basically wastes works and misses good results. And you don't really want to run separate algorithms and combine the results later, but you want to build execution plans that filter, score, and rank in a single pass. And I think this is a really interesting pattern as well. Like when you can combine it, you probably should think about combining it. Another really interesting thing they have done is basically strategic caching. So most just use something like Redis. They have built their own solution on something like EC2, I think. And at some point when you're building an application, every database needs a cache in front of it. And since they have built their own logic, they can do a little bit more than just a regular cache, because you can build something like two-tier caches. So basically you have memory for really hot data, and then you have local disk for warm data. And this can reduce cloud storage costs while also preserving the performance. And you can also not just cache the raw data, but also cache intermediate results, which are expensive to recompute. And by building your custom caching solution or a custom cache, which takes a little bit more work, you can find a caching strategy which really aligns with your workload. So what's frequently accessed, what's really expensive to rebuild, and what data is accessed together. And I think as we start to build more and more with AI, and especially also with agents which access our own data, this will become more important, because we don't really want to hit our production database all the time. Yeah, I think that's it for this week. We will have one more episode in search next week, and after that we will be moving on to a new season on MLOps. So I'm excited for next week. As always, if you like the episode and you're still listening, leave a subscribe or leave me a comment. Also, if you have any suggestions in terms of guests who you would like to have on, let me know in the comments or send me a message on LinkedIn, Twitter, Blue Sky. Otherwise, I will catch you next week. See you soon.